So let's now think about some of the properties of the naive Bayes and how it compares with the full Gaussian. As we saw before, if we have a full Gaussian distribution in multidimensional space, so x, basically the data point xi is a vector, then we have to use the full formula for the Gaussian, which is basically includes using the full covariance matrix. There's a term in the scaling factor at the front, and there's also an inverse covariance term in the exponential expression, and x and the mean are both vector quantities. We can, of course, use that representation, but the problem is it's difficult to estimate the covariance matrix, and that's why we will end up trying normally to do an assumption that we have independent features. So it could be that we ended up with some data set and we estimate the covariance and it looks something like this. The important thing to notice, in this case, along the leading diagonal, we have the variance terms, the variance for feature 1, feature 2, this is for two-dimensional data, and we have in this case a couple of covariance terms. Now in naive Bayes, basically we're just saying everything is independent and we only use the marginal Gaussian parameters. In other words, we have non-zero values along the leading diagonal only, and the covariance terms are 0. And like I said, this leads to basically to the fact that we have independent features. That's the assumption. And it makes it a lot easier to estimate these parameters, basically, right? So imagine now we're looking at a data set and we're going to look at it from the perspective of the Bayes classifier, because I think this is quite enlightening. If we've got some data that looks like this, we're going to train the Bayes classifier on this data. We have two classes. We have this class of the red data, which is class 1, and the blue data, which is class 2. And then we're going to basically run the classifier and see how it works on some testing data. And what we're going to find is typically something like this is going to happen. We find in this particular case, our naive Bayes classifier is not able to distinguish these two classes properly. And the reason is because it cannot put in a boundary and an angle. It's stuck basically doing a vertical boundary in order to try to make this classification. And the reason for that is the way it's actually representing the data, or the way it sees the data. So what's going on? So actually, if we look at the data that we start with here, and we represent this, let's say the red distribution now by the marginal distribution, then what we're saying is we represent the x data by its mean for the x feature and by its variance, and then independently, and that's the important thing, we represent the y data by its mean and its variance. And if we actually plot out now what that corresponds to, if we generate data from it, what we'll see is we'll end up getting a representation, or if we sample from that Bayesian, naive Bayes representation of the data, what we see is x and y are now independent, and consequently, if we sample from it, we end up with samples which align with the axes. So the cloud is now aligning with the axes if you look at the principal component of the cloud. So it's not able to represent the fact that this is actually correlated data, because that's the assumption. It assumes it's not correlated. It assumes that it's independent between x and y. But actually it's not independent between x and y, otherwise it wouldn't be at this angle. But that's what naive Bayes is seeing in the data. It's seeing this data where we have effectively independent x, independent y, and therefore, as far as it's concerned, this is what the data's looking like if we reconstruct it. So consequently, if this is what the assumption is that the data looks like, where's it going to put the boundary? Well, it can only put the boundary. It's going to put a vertical boundary here to separate these two classes out, obviously, right? So, and we can actually do that by training the naive classifier and then running it on uniformly distributed data that covers the entire plus or minus 10 on feature 1 and plus or minus 10 on feature 2, and run it in and see how the classifier classifies that data. And what we'll end up doing is we'll end up classifying and showing up the boundary that the thing is generating. And as we can see, it's just a straight line, so it's not at an angle.